Marhaba. Okay, in the previous sessions we've seen what is a countable set. It's a set which is finite or countably infinite, and countably infinite sets are sets which can be put in bijections with the set of natural numbers, which means those are the sets which we can list all their elements. The first element, the second element, the third element, and so on. But we haven't seen so far a set which is not countable or which is uncountable. Okay, so in this session we want to see the very first example of a set which is not countable. And you see, what does it mean to be not countable? It means it's not finite, so it's an infinite set, and moreover it's too big to be to list its elements. So it's bigger, its infinity size is bigger than the size of the natural numbers. We cannot list the elements of an uncountable set. We cannot have a bijection between the natural numbers and an uncountable set. So today what we want to show, in this session we will show that the real numbers are uncountable. Okay, uncountable. Okay, in other words, we mean that the set of real numbers is an uncountable set. Okay, clearly the set of real numbers is infinite, but it remains to show that we cannot have, it is impossible to have a bijection from the natural number to the real number. So this means that it's impossible. Okay, let me say, what does it mean that R is uncountable? It's impossible to have a bijection, say some f from the natural numbers to the real numbers. Okay, it also means it's impossible to list all real numbers. So there's no way to start saying numbers like 0, 1, 0.2, 0.3, pi, e. It's impossible to start listing it and list all of the real numbers. No matter which list you have, it will miss some real numbers. Okay, this is what we want to show today. Okay, but we will first show that, so this is the theorem we want to show. So remember, we talked about intervals of real numbers, so remember that this interval from 0 to 1, this set is the set of all real numbers x such that x is strictly bigger than 0 and strictly less than 1. Okay, this is what we mean by this set. So in the real number line, if this is the real number line, then this set, this is the 0 and this is 1, and we mean this all the real numbers lying between 0 and 1. Okay, so we want to show that clearly this set is infinite, because you have, for example, 0.1, 0.11, 0.2, 0.22, 0.2222, 0.3, 0.4, 0.5, 0.55, 0.56. You have infinitely many numbers here, and what we want to show that this set is actually uncountable. And once we establish this, then clearly R should be countable, because if you can list all the elements of R, then you can list all of these elements. But we will show that we can't list these elements. So we want to show that this set, the set of all real numbers between 0 and 1, is uncountable. Again, uncountable means there's no bijection with the natural numbers, which means we cannot list the elements. Okay, so this is our theorem. So this is theorem, and we want to show that the set of all real numbers between 0 and 1, the interval of Okay, the interval of real numbers between 0 and 1 is uncountable. Okay, and the idea of the proof is due to the great German mathematician Georg Cantor, who lived from 1845 till 1918, and this argument, his proof, is called the diagonalization argument. You will see why it's called the diagonalization. Okay, so proof. Let's start proving this. We want to show that that the set is uncountable. This set is uncountable, which means we cannot list all of its elements. So we will prove this by contradiction. Suppose, okay, for the sake of contradiction, so suppose for contradiction that this set is actually countable. That is countable. So this set is countable. This means that the cardinality of this set is equal to the cardinality of the natural numbers. Okay, which means that there exists a bijection. Right, what does it mean that two sets have the same cardinality? This means that there is a bijection from the first set, or let's say the second set, to the first set. Okay, but what does it mean to have a bijection whose domain is the natural numbers? It means, again, you can list all the elements in this set. So we can list all, okay, elements or real numbers in this interval in 0, 1. Again, this is our assumption. We assume that this set is countable, so we can list its elements, and remember that our goal is to arrive to a contradiction. So say that say R0, R1, R2, R3, R4, and so on is a list. So this is a list. So all of this is a list of all real numbers, okay, in this interval between 0 and 1. Okay, now we want to use the decimal expansion of every real number. So let's say we take a break from this proof. I want to give a particular example of the argument and then get back to the proof. So suppose that R0 is expressed as 0. So remember, what is R0? R0 is a number between 0 and 1. And we want to use its decimal expansion. So its decimal expansion has the form 0. Say 2, 6, 7, 9, 1, 1, 3, 4. I don't know what is, but suppose R0 is this number, and suppose R1 is this number, say 0.5, 7, 1, 2, 3, 6, 8. I don't know. Okay, so this is a decimal expansion of R1, and suppose R2 is given by 0, 5, 3, 1, 1, 1, 4, 5, and so on. And say, okay, one more example, R3 is 0.789 26129 whatsoever, and say the list continues forever, and we claim that this list lists all the numbers between 0 and 1. Okay, again, okay, we assume that this list contains all the real numbers between 0 and 1. Now we have a question. Consider the number, let's call it S, where S is obtained as follows. It is 0 point. Now you look at the first, I want to construct a new number, call it S, in the following way. you look at the first decimal place to the right of the decimal point of the first number, and if it's 2, you put here 3, and if it's not 2, you put 2. Okay, now to obtain the second place here of S, you go to the second number in the list, which is R1 here. You look at the second place of its decimal expansion. If it's 2, you put 3, and if it's not 2, so here it's 7, it's not 2, you put 2. Okay. Now to find the third decimal place, you go to the third number in the list. Okay, so maybe it's easier if I call these R1, R2 just. Okay, let me call them R1, R2, R3, R4, it doesn't matter. Okay, now, okay, so what we are doing, we are creating a new number as follows. The first decimal place of this number is obtained by going to the first number in the list, checking its first place, and if it's 2, we put it 3. If it's not, we put it 2. But since it's 2, we chose 3 here. Now, to obtain the second place of S, we go to the second number of the list, and we go to its second decimal place. And if it's 2, we put 3. If it's not, so here it's not 2, it's 7, we put 2. To obtain the third, again we do the same. We go to the third number in the list. We go to the third place of the third number. And if it's 2, we put 3. If it's not, like here, it's 1, it's not 2, we put 2. So here, this is 2. And we continue in this form. To obtain the fourth place here, we go to the first number. We go to its fourth place, so it's this number. Since it's 2, we put it 3, and we continue in this point. Now, what's so special about this S? Look, this number S is not equal to R1 because the first place here is 3, while the first place here is 2, and so they are not equal. So S is not equal to R1. So we know that S is not equal to R1. Now, what about R2? Look, S is not equal to R2 because the second place in R2 is 7, while it is 2 in S. So again, that S is not equal to R2. Similarly, S is not equal to R3 because the third place of S is 2, while the third place of R3 is 1. So they differ in the third place. And S and R4, they differ in the fourth place. Look, here it's 2, here it's 3. So this means S is not equal to any number in the list, in our list. Okay, but notice that, what do you know about this number S? The least it could be is 0.222, which means it's strictly bigger than 0.2, and the largest it could be is 0.3333, which means that, say, it's strictly less than 0.4. And 0.4 is strictly less than 1, and 0.2 is strictly bigger than 0. This means that S belongs to this interval. So S is between 0 and 1. And you see, this is a contradiction because we assume that this list lists all the real numbers between 0 and 1. But we managed to find a number S which is between 0 and 1. But it can't be in the list because it's different from R1 in the first place, it's different from R2 in the second place, it's different from R3 in the third place, and so on. And this is the diagonalization argument of Cantor. So if you want to write this in a general way, so again, assume we have a list of all the numbers and say the list is R1, R2, and we can write R1 as 0.A11, A12, A13, A14, okay, and so on. So assume this is the decimal expansion of R1, and assume this is A21, A22, A23, A24 is the decimal expansion of R2, and this is the decimal expansion of R3, 0.A31, A32, A33, okay, A34, and so on. R4 is 0.A41, A42, A43, A44, and so on. So what is these Aij? So, and you keep doing this for every number in our list. So notice that Aij is just a decimal digit, so it's a number between 0 and 9. Okay, like in the example, this was A11, this 6 is A12, 7 is A13, and so on. 5 is A21, and so on. 7 is A22, 1 is A33, and this 2 is A44. Okay. Now, so we assume that this is a list of all the numbers between 0 and 1, and then we expressed every number using its decimal expansion, and then we consider the following number. So consider the real number S, where S is 0. Say B1, B2, B3, B4. Okay, how did we define BI? So BI, for example, how do you define B1? You want B1 to be different from A11. So we look at the diagonal of this. We look at A1, A22, A33, A44, and we want A11 to be not equal to B1, where B1 is the first place of the decimal expansion of S, and we want A22 to be not equal to B2, and this is not to be equal to B3, and this is not to be equal to B4, and so on. Okay, so how do we define BI? By saying BI is 3 if AII is equal to 2. So if AII is 2, if the diagonal element here is 2, we make this element BI 3. And we want them to be different. And if AII is not equal to 2, we will make BI 2. Okay, so if the diagonal element here, say if A33 is not equal to 2, then we want to make B3 to be 2. Okay, in this construction, it follows, if we define this number S in this way, it follows that S is not equal to Ri for all I, 1, 2, 3, and so on, right? S will not be equal to R1 because the first decimal place of S is different from the first decimal place of R1, and the second decimal place, which is B2 of S, is different from A22, which is the second decimal place of R2, and the third decimal place of R3, which is A33, is different. It's not equal to B3, which is the third place of S, decimal place of S. Okay, why is this? By construction, because we let the ith place of S to be different from the ith place of Ri. Okay, so, and again, S is at most is strictly less than 0.4 and strictly bigger than 0.2, which means that S belongs to this interval, right? But S is not in the list. In the list we started with, in which list? It is in the list R1, R2, R3, and so on. Okay, let me just show you what we just sum up everything, we assume that the interval of real numbers between 0 and 1 is countable. If it's countable, it means we can list all, okay, so we can list all real numbers between 0 and 1 in this form, R1, R2, R3 up to R4, and you can just neglect this one. R1, R2, R3, R4 is a list of all the numbers between 0 and 1, and then we expressed R1, R2 in terms of their decimal expansion, and using this decimal expansion we constructed a number which turned out to be in the interval between 0 and 1, but it's not in the list. It's not equal to R1, it's not equal to R2, it's not equal to R3, and this contradicts that our list lists all the numbers between 0 and 1. So this is a contradiction. So we have a contradiction. Contradicting what? That we have a contradiction. The contradiction is that in the very beginning of the proof we assume that we have a list of all the numbers between 0 and 1, real numbers, but apparently we found a number which is the number s constructed in this way. So this is how we construct the number s, and this number s is not in the list, it can't be in the list, and it belongs to the interval between 0 and 1. So this is a contradiction, and we can conclude that, so therefore the set of real numbers between 0 and 1, or real numbers strictly bigger than 0 and strictly less than 1, is indeed uncountable. So this is a set which is infinite, and we cannot list its elements. It has too many elements to be listed. We can't list the elements between 0 and 1. Okay, what we showed that suppose you can list the elements between 0 and 1, then you find an element between 0 and 1 which is not in your list. It's impossible to list the elements, the real numbers between 0 and 1. Okay, so this is the end of the proof. So what did we show? So remark, we showed that the cardinality of the natural numbers is strictly less than the cardinality of this interval. Why? Remember, how did we define strictly less? By saying there is an injective function, so you can think that of an injective function from n to n, but it's impossible to find a bijection. Because if you have a bijection, then you can list the elements of 0 and 1, and we just proved we cannot list them. Okay? So you see what is this saying? That there are two infinite sets, this set and this set, and the size of an infinite set is strictly bigger than the size of another set. This means that we discovered two levels of infinities. One infinity is bigger than another infinity. Okay, let me fulfill the initial promise. So corollary, the set of real numbers, R is indeed uncountable. Okay, proof. I will sketch the proof. First, notice that the interval of real numbers between 0 and 1 is a subset of the set of real numbers, right? Because every element in this set is a real number, so every element here belongs to R. And it follows that, so suppose that R is countable, then we can list the elements of R, but if you can list the elements of R, you can list the elements between 0 and 1, and we just proved that we cannot list the elements. So this means that R can't be countable. So it follows by our work above that R is uncountable. Okay, this is proof by contradiction, because if it were countable, then the interval 0, 1 is countable, and this is not true. We just proved that it is uncountable. Okay, so this is the sketch of the proof. So the end, we proved that, so this means that the cardinality of n is strictly less than the cardinality of R. In other words, R is uncountable. Uncountable means there is no bijection between n and R, which means, okay, this means we cannot list all the real numbers. There are too many real numbers to be listed. Okay, this set is much bigger than the natural numbers. Okay, so what did we prove in this in these series of sessions? That the cardinality of n is equal to the cardinality of z. It's equal to the cardinality of q, right? This means that there is a bijection between n and z. There's a bijection between n and q, the rational numbers, which means that we can list the elements of the natural numbers, we can list the elements of the integers, we can list the elements of the rationals, but all of these is strictly less than the cardinality of R, which means there is no bijection between the... We define this to mean there is an injective function from n to R, but there is no bijection from n to R, which means we cannot list the elements of R. So here these can be listed, the elements of these sets can be listed, but here it is impossible. It is impossible to list elements of R, to list real numbers. Okay. Precisely speaking, this means that there is no bijective function, there is no bijection f from the natural numbers to the real numbers. Okay, so let me finish by again saying this means that we have two sizes of infinity, one size which is smaller than the other in the sense that one infinity can be listed and the other is too huge to be listed.